The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone. This is William Makant. I'm just going to give another minute so that the latecomers can make their way through the internet piping. Okay, I guess I'll give this a start. I'll do a presentation and then I'll take questions at the end. You should be able to ask questions through the dialogue that you have, the panel dialogue that you have. Okay, well, in this presentation, I'm going to be talking to you about residential fire suppression and how it works within the building regulations. About myself, I am William Makant. I'm the CEO of Plumis. We're the UK inventors and manufacturers of the only electronic residential watermist fire suppression system in the market, which now has more than 10,000 installations, and these vary from sheltered housing to private homes, either for code compliance or for elective safety enhancement. So the agenda for today for this presentation is firstly, what is suppression and when is it used for with respect to the building regulations? What are the functional requirements of the building regulations? And these often are confused with guidance documents. So then we'll go to the guidance document and what do they really say as opposed to what most people think that they say about suppression. And then the most common types of suppression and the difference in operation between them. The key objectives of suppression standards and their performance requirements. And that's the part where stakeholders should really be versed in with respect to suppression. The difference between compliance and certification, which is also frequently a confusion, and an explanation of other suppression industry jargon. Then I'll talk about, following Dame Hackett's Building a Safer Future report, about fitness for purpose. And finally, I'll just talk about ongoing development in the residential fire suppression world. So first, let's start with first principles. What is the purpose of suppression? There are only two key objectives really when you deploy suppression for life safety, and this presentation is about life safety. So the first is to limit the rate of growth of a fire so that suppression, effectively the definition is that the growth is reduced. And the second is to avoid the flashover, where the temperature of the room is so high that every item in the room combusts. These are really the only two things, and everything that comes into meeting the functional requirements of the building regulations are a function of these two key purposes of suppression. So I'll explain this a bit more. In your typical fire growth curve, you firstly have ignition and there's a period of incubation. The fire then progressively grows as it spreads. There's a progressively higher heat release, the amount of power of the fire, which is usually measured in kilowatts or megawatts, which is the heat produced by that fire. And as you can see, this grows parabolically. This is a function of time squared. And of course, there's a moment during the fire growth that if the person is trying to escape, there's a limited time until they can do that, and at which conditions become untenable. That is the tenability limit. And the whole point of suppression, of course, is that it avoids the activation. It avoids the reaching this tenability limit, so that the available time for escape can be extended. So when is suppression used? Well, there's a few ways in which it's used in the building regulations. The first is to meet functional requirements, and these are B1 to B5 of the B schedule of the building regulations. And the second one is to be used as a compensatory measure, where the functional requirements are being breached or not met by the design of the building without the use of suppression. And then the third is, which is becoming more common, which is to enhance the safety of a building that would be otherwise compliant with its current design. So going into what is meant by the functional requirements, there are 5 functional requirements, B1 to B5. I'll go only through those really truly relevant for suppression. The first one, B1, is that there has to be a warning of fire, and there also has to be a means of escape to a place of safety. And the first clarification that I make is that this means that the first clarification is that a building has to comply with the building regs and not the suppression system. And I mention this because this is something which is often incorrectly asked for us. The suppression is just a tool to contribute to make the building compliant to the building regulations. And although protected escape routes and alarm systems are the most typically used tools for meeting B1, suppression can also contribute to that. And how does that happen? Well, the activation of suppression is increasing the period of tenability in the room. So you're effectively increasing the time that the occupant has to escape through that means of escape. The activation of suppression is also a possible mean to warn occupants of a fire as well, whether the suppression system is linked to an alarm system or whether it integrates an alarm system within its functionality. Another clarification I should make, sorry, let me go back there. Another clarification I should make is that the means of escape is not just the stairs and the corridors. It is every compartment which is part of the escape route. We've unfortunately seen too many requests for suppression systems to be used only in the stairs or corridors because that's what's been interpreted as the means of escape. However, there is no fire load typically in stairs or sterile common corridors. It is the areas of occupancy where there are fire loads, and these are the ones that need to be protected when they are part of the escape route. So this is a typical misunderstanding. So then I'll talk about B3 as well. It talks about the internal fire spread. Again, where as per suppression, we're avoiding a flashover. It's where temperatures are too high, and as a result of the temperatures being too high, there's the need to ensure that the fire is contained in the compartment of origin. So again, another way to meet functional requirement of the building regulations has historically been through the use of passive fire protection. This is the plasterboard or fire-resistant doors to hold the fire within, contain it within that compartment. However, as we can see in these 2 examples, there might be breaches in this compartmentation, which then compromises the ability to meet B3. However, so suppression can be used as a secondary layer, basically, to ensure that the fire will not spread beyond the room of origin, where passive has already been used. Okay, so now if I cross the objectives of suppression with the functional requirement of the building regs, we can see how, for example, the limit in the growth rate of a fire buys time for the egress through the means of escape, and with that we're contributing to the building meeting B1, and by avoiding flashover we're helping the role of passive fire protection, which is avoiding the fire spread from the compartment of origin, which is contributing to B3. So a second way to use suppression within the building regulations is to act as a compensatory measure. So what does this mean? It means that if the design of the building as is without suppression cannot comply to the functional requirements, then suppression can be used to compensate for that and return it to a compliant status. For example, if the building has been designed with a single escape route, or the escape distances are longer than what fire engineering considers safe, then suppression can be added, and by delaying the fire growth, the available time for escape is extended so as to meet B1. Similarly, B5 talks about the access to firefighting engines, for example. And when there's a limited fire engine access, suppression can then be used to extend the time which firefighters have to reach the building and contribute to the fire suppression exercise. So this is known as typically known as the 45-meter rule, and it is a typical use of suppression as a compensatory measure. And then we have another example, which is open plan layouts, where a flat might have a living room and a kitchen together, which are part of the escape route. And this is where there are fire loads, and this is where suppression, again, extends the time that occupants have to escape while the fire is developing. In all cases, these are the functional requirements that might be met by relying on firstly, the fire growth being retarded and or flashover being prevented. Unfortunately, these first principles of suppression are frequent, and of the building functional requirements of the building regulations are frequently forgotten within the multitude of guidance documents available. And when suppression is specified, it's also not very common at least, to find the statement of why is it being used, what objective is it trying to achieve, why is it being used as a compensatory measure, for example, unless really a fire engineer is involved, which is really unfortunate. So this table is really just a summary of what I've just stated about how suppression and the functional requirements work together, and through the limiting the fire growth as well as the avoidance of flashover. However, it's also important to note that nowhere in the building regulations is the expectation that occupants will remain in the room of origin and that tenability will be maintained indefinitely. It's assumed that the occupants are mobile always and that they will escape. There are systems that are now being designed with this additional objective in mind, regardless of whether the functional requirements in the building regulations require them or not. So this is the third trend that I'm talking about, which is enhancing the safety of an otherwise compliant building. It's not only is it an additional layer for improvement of B1 and B3, where it's already technically compliant. This is where the reduction in height of buildings above 11 meters to have suppression as a new build. But it can also protect those who do not have the mobility to escape from the room of origin. This is what it is beyond what is required from the functional requirements of the building regulations, but it is present in some guidance documents, such as that of the Specialized Housing Guide. Whoops, sorry. So I'm going to use an analogy here to explain what is the difference between the building regulations and guidance documents. And hopefully this analogy will help. So the building regulations are the performance requirement. In this example, the performance requirement here is get safely from A to B. So approved document B is a guidance document, and it would say in this case that a ladder is an example of a tool that has been historically accepted as being used to get from A to B. ADB also states that if using a ladder, it is best practice to use the standardized ladder that fits the ladder stencil, which is ensures that a ladder will work best as a ladder. So which are the common documents, guidance documents, which specify suppression? Well, ADB recommends the use of sprinklers, and BS9252 recommends the use of sprinklers or watermist. And what is the difference between the two? Well, it's just a different level of sophistication between the two documents, where BS9252 is diving more into the world of and the details of the world of suppression and of fire engineering. So both are based on the same principles I stated early on. The difference is that BS9991 has more detail on the types of buildings and the types of suppression systems that can be used. And yet another clarification, one does not have precedence over the other. Both are just guidance documents based on historical practice. So as with the ladder example, both require common sense and due diligence. Neither of them is the law. It's only B1 to B5, which are the law of what I've talked about today, which is basically like the ladder. The law is the performance requirement of getting from A to B, not of using the ladder in itself. The ladder is one of the ways in which you can achieve that. And this is just an example of a table extracted from BS9991, showing the more granularity in the use of suppression. So let's start going a bit deeper and starting with the oldest of the automatic suppression methods, the sprinklers. So firstly, for residential purposes, they only exist as wet pipe, which means that the pipes are charged with pressurized water all the time, and the nozzles are activated by mechanical means using a thermobulb. It's also the means that this also means that because sprinklers are primarily driven by gravity, the nozzles tend to be mounted high, so it's usually close or on the ceiling or close to the ceiling, so that gravity can help in the wetting process. And so how are sprinklers defined? How are they coded? Or better still, what are their stencils? These are some of the more common standards, and I'll go into a bit more detail of what the difference between them are later on. So the sprinklers you can see is the first patent for it was in 1882 by Mr. Grinnell. And as you can see, today's nozzles don't look much different from what they used to do. And that is in part due to the very smart design, the brilliance of the design, but it's also in part due to once it was coded into a standard, its scope became very specific and finely and narrowly defined. And then that limits how much the sprinkler itself can vary because before it becomes something other than a sprinkler, and therefore out of the scope of the standard that guides it. So on watermist, on the other hand, internationally, its definition tends to be much broader, although for domestic systems in the UK, it's still currently only a wet pipe, but more internationally, its variations in how it's deployed are much wider, and how it's therefore implemented, depending on the application, is also much wider. The key definition for watermist is really that it is the use of small droplets, smaller than 1 millimeter in diameter. I'll go into a bit more detail later. And again, how are they coded? There's a number of standards. I'll go into detail what each one of them means. So again, for watermist, the key objective is that you're using smaller droplets, and the whole idea is that then by using smaller droplets and creating a larger surface area, you can leverage the best of the sprinkler, which uses water, and the best of gaseous systems, which create an inert atmosphere. And therefore, it has a higher compatibility with a wider variety of fires than either of the two methods by themselves. So I'll go into a bit of some physics to explain the difference between them. This is Ragnar Wiggers. He's the past chairman of the International Watermist Association, and who highlighted to us how Archimedes works well for watermist, while Newton works well for sprinklers. That was very useful and stuck with us. So sprinklers produce large droplets, and the whole idea is that the nozzle located on the ceiling or high up in the room allows gravity to pull it down and wet surfaces. And the fire cannot progress well over wet surfaces, so it gets suppressed. The large droplets also allow it to go through the hot layer or the updraft of the hot combustion gases without too much loss of water through evaporation. So if the same principle was expected from watermist, on the other hand, The much smaller drops of water would result in a significant portion being lost due to evaporation in the hot layer, and even against the updraft of the hot combustion gases. So instead, water mist nozzles are designed so that the small droplets can be drawn to the base of the fire by the natural air draft created by the pumping action of the fire. And when mist reaches the base of the fire, it evaporates, it creates an inert gas layer when it's converted to water vapor, and in the process extracts heat from the fire. So the consequence is that there's less use of water for the same suppression effect when using water mist because of its different means of operation. There is, of course, arguably an environmental benefit because of the reduced water discharge and therefore of runoff. But it's also important to highlight that even sprinklers are beneficial, that there's many studies that have shown already that the discharge of sprinklers result in a lower carbon footprint than compared, not surprisingly, to a fire which is left to destroy a whole property or even with firefighter intervention. Okay, so for water mist to be deployed on the base of the fire, there are many different ways in which nozzles are placed and designed and located, and these really depend on the application. Some of these might resemble sprinkler heads in which the nozzles are pendant and they use a heat sensitive element. But there are also applications where the nozzles are placed on the floor, and this is common for the protection, for example, of helicopter in hangars, so that the mist is closely located and the mist layer is placed at the base of close to the ground and close to the base of the fire. So there are also electronically controlled nozzles, and directional nozzles, which is what we manufacture, and these are activated by detection systems, for example. The objective, which is common with all these nozzles, is just to position the discharge of the mist to maximize the deployment locally of mist at the base of the fire, as opposed to be limited to being located on the ceiling where, like a sprinkler would, and relying exclusively on leveraging gravity and leveraging the ability to wet surfaces. Okay, so I'm just going to go a bit more detail in why would one use an electronic nozzle. So the first idea here is to leverage the use of detection, which has a much faster reaction time than a mechanical system. It's an electronic, much less thermal inertia, or different sensing methods, not only heat, but it could be smoke. And that generates a first knock and also raises the alarm that contributes to the means of escape. Then the fire can be verified as a true fire, which is then as a dangerous fire, and that's where the second knock comes off. And then there's the discharge of water. And the whole objective here is to ensure that the fire is as small as possible at the moment of discharge. And the objective here is that there's, as a result, even less water required to obtain the same suppression effect. But at the same time, there's a smaller fire to be tackled so that there's less smoke and less heat in the room, which further extends the tenability to the occupants in the room. Okay, so I'm now going to go into a bit of the key concepts of standards. The first is that there are typically three objectives of standards, but they're not necessarily present together at the same time. So the first is the consistency in design, and the objective here is interoperability. So you can think of an M5 screw, for example. The standards allows screws from different manufacturers to work seamlessly as custom threads, one for each. A type of thread for each manufacturer would certainly be a hassle for all of us. The second is one that seeks consistency in performance or consistency in quality. And looking back at the ladder analogy, it would be as the code developed to test and validate that the load of each each step can support on a ladder is adequate and consistent. And by the way, there's a standard for that. It's EN 131, in case you're curious. And then there is the third C. It's the consistency in practices. So this is what we would call a code of practice, and this is probably the most common in the UK for the suppression world, where it documents the best practices of installation and maintenance, for example. And this is exactly what BS9251, which is the most commonly cited standard, is about. So it's important that when a standard is referenced, that it's very important to understand which of these objectives are really being addressed by the standard. BS8458, for example, the UK watermist standard covers mostly B, with some very little guidance on C. It in fact defers the C part of it, the code of practice, to the manufacturer's installation manual, and that's quite different from the sprinklers, of which BS9251 is more of a C. It's a installation and maintenance guide. So in this presentation, I really want to focus on B, the performance requirements for suppression, and helping define whether it's fit for purpose. This is because I find it really relevant for stakeholders. It's information that's beyond designer and installers of system. It's key to understand some of these performance requirements, so that stakeholders can understand whether the system will work once installed in the field. So I'll break down the performance requirement into three main items. The first is that there's a fire test, and these requirements are common in BS9251, or covered through BS9251, BS9252, BS8458, the different, or the YEN 12845, the sprinkler standard. I'll go a bit more detail into that later on. But the first item here is the fire test, and this is where the system is tested with a standardized, stylized furniture setup. Then there's the verification of the water supply flow and for that installation, and whether the installation will provide the flow of water that's demanded from the system, from the nozzles activated. And finally, the verification of the piping of the system, whether it will allow the water being supplied by the water supply to be deployed in enough volume as required by the nozzles. So let's go first through the fire test, which is internationally used to validate a suppression system. Let's see if this plays. Indeed. So as you can see, this tries to represent the furniture in a standardized, repeatable way. On the left, you have a free burn, and on the right, you have a suppression, where it's in this case being done by a sprinkler. And as you can see, the whole idea is that you're capping the growth of the fire. On the left, if you were to let the fire grow, flashover would be reached, or that doesn't show it on this video. And just very clearly, as this video shows, that suppression is not necessarily extinguishment. It's why it's called suppression. It is literally to cap that fire growth and avoid it growing at the rate that it would were it a free burn. Okay, my second item is with respect to the adequateness of the water supply. So in a correctly designed system, the water supply will match the demand for all the nozzles that are expected to operate in that installation, and they're up to a maximum of 4. So there might be the assumption that only one nozzle operates. In fact, the standard as to between 1 and 4 nozzles might operate, depending on how many you have in a room. So in this case, we have 3 nozzles in the room. All 3 nozzles should be expected to activate. And when we do have a fire and all 3 nozzles activate, if there's too little water supply available, what will happen is the fire will grow. Whoops. Because there's overall less water available for each of the nozzles. As the nozzles activate, there's less water available per nozzle when compared to the water supply that was the flow that was tested on the fire test, which isn't necessarily not typically run with more than 2 nozzles. So all residential tests are run with 2 nozzles, but if there are 3 nozzles in a property or 4 nozzles in a room, then the water supply should be enough to supply all 3 nozzles or 4 nozzles being activated. And this is key because as opposed to a commercial setting, a domestic setting won't necessarily have that water available, which is why suppression systems sometimes need tanks. Okay, the second is the need for hydraulic calculations. For installed system to perform, the piping has to be of sufficient diameter or the length of limited length as not to result in too much restriction from the water flow, which again would limit the flow of water from the nozzles. So when compared to a fire test. So again, if we have the nozzle that does not have the amount of water that is expected from a fire test, then the result is that there is a risk of a larger fire than what was tested in the verification test, which verified that it would create the tenable conditions in the room. So in the end, the installed system will not replicate the tested system on the stylized fire test. And this is a requirement to comply to the standard to deliver the necessary amount of water. Okay, so I'll go a bit more into the standards now. The most important really is the difference between certification and compliance. And first, there are standards like a BS, British Standard, an FPA, National Fire Protection Association, and European norm, the European standard. These are examples of national or international standards. These have been written by committees, and they're usually part of a committee which is part of a country or a continent, in the case of the UN, of course. And product systems in these markets can comply to those standards. So what I mean is that they can state that they're compliant to these standards, against these standards. And where there is a third-party verification of it, then there is a certificate of compliance, or there's a verification of compliance with that standard. So the key thing is that this certificate of compliance or verification, this is not certification. They sound similar, but they're very different. So for certification, these are provided by independent labs, which are not limited to specific geographies, although some might be. But some example of these labs are UL, BRE, FM, CNPP, and they might have international, or they frequently have international reach. And their standard example of their standards are UL, LPS. LPS is a standard written by the BRE. And all these labs basically carry out fire tests of components, of systems, and provide certification of these systems against the standards that they themselves write. This means that they have the autonomy to write their own test protocols to ensure that they have properly scrutinized that system or component, which may be well beyond what a national standard writes, yet has coded into its standard. So this is another type of third-party performance verification, but this one is indeed a certification. So there's a clear difference between the two, and obviously certification as opposed to verification of performance is the ideal. It's a proper third-party verification of suppression. I guess the first caveat is that it's not mandatory to have certification of domestic systems. It is very common to have them in commercial systems, but that's because it's a typical minimum requirement from insurers. It is nevertheless desirable for domestic and residential applications because it is third-party demonstration that the system will work as intended, even on the long term, on the life cycle of the product, and it is declared by somebody else who still has skin in the game because they're effectively now technically underwriting that system by certifying it. And there is standards for nozzle, pump, controller, and installation, but it gets a bit more complicated than that. So I'm not going to dwell too much on this table because this could take all day. It's just really to highlight that there are many types of standards for all the different components of the system, and sprinklers do not have a system certification. It is just the nozzle or the other components in it. And there's only a very small proportion of the applicable standards that apply to suppression that really get cited on ADB and other guidance that there is publicly available. There's much more than just a recommendation of how the system should be installed. It's also how the system should be tested and verified to be durable and perform over its lifetime. It's also useful to note here that some standards have not yet been published, even for sprinkler systems. And that shows, and this is for residential, and this just shows that it's a result of really not having much interest from manufacturers to get them certified. It's also important to highlight that that asking for compliance is not the same, is not the only question to be asked. Is that certification of components and certification systems are also an important question to be asked by stakeholders. Insurers certainly ask them. So things are not much different for watermist. The only difference, of course, is that watermist has not been in the market for as long as sprinklers, which means that there's less standards published for watermist than there is for sprinklers, but this is to date, of course. This is changing. There's even now EN standard recently being published for watermist. As you can see, there's also system standards, and there are also many standards published by UL, FM, and VDS and other European labs, given that there's a higher presence of watermist manufacturers in Europe. Commercial and industrial watermist applications are also more common. So sometimes even commercial systems are used in residential settings just because they have been certified and an insurer is demanding it as a higher level of confidence and reliability. We as a manufacturer, we're actively pursuing certification at UL in the US for our domestic system, given that there's none available in the UK for us. And there's no currently fully certified domestic water suppression system in the UK market at all yet. Okay, I'd also like to explain a few other jargons within the suppression industry. First, just to clarify the difference between domestic and residential, engineered and pre-engineered, and how innovative and alternative systems works within the existing framework and the challenge for innovation in the fire sector. So this is a residential building with multiple dwellings. A suppression system might be a residential installation, which includes one pump and tank for these many dwellings. Yet a residential building may also have a number of domestic installations. This is common in refurbishment, in retrofit, or even to address an inner room scenario where the building originally did not require suppression. And although it's rare, it also could be done in new build where every flat has a domestic system in it, which becomes a multi-domestic installation instead of a residential installation in a residential building. The key is that the definition of domestic is a system that protects one or two dwellings, not more. However, a multi-dwelling residential building, due to its higher risk of occupants, and that's obviously because of the longer escape route and the delayed firefighter access, it's typical for there to be additional requirements to be recommended to compensate for these extended distances, for these additional risks. And this is, again, suppression being used as a compensatory measure, or additional measures of suppression being used as a compensatory measure. These include running suppression for 30 minutes instead of the typical 10 minutes for domestic, and also, for example, having a secondary power supply for additional resilience. Then the resulting situation could be of a domestic dwelling in a residential building meeting residential requirements. I hope that is clear of the separation between a domestic building, domestic installation, and a dwelling and a domestic installation. Okay. Oh, sorry. So what does the pre-engineered mean? Well, pre-engineered just means that the design work of the hydraulic calculation has been done by the manufacturer. So the pipe length, diameters are all pre-established in the system. The advantage is, of course, that there's a cost, effort, and risk saving in designing the system, because that's already been predetermined by the manufacturer. There is one less thing to worry about from the installation point of view, and therefore in terms of the performance requirement for the suppression system. But there is the trade-off, which is that there is a limited coverage in terms of area. You cannot cover a shopping center or a whole high-rise with a single residential pre-engineered system because of the limited pipe lengths. So this tends to be domestic systems, which are pre-engineered and are limited to 1 or 2 dwellings. Okay, now talking a bit about innovative systems, which is for what we as a company were about. As I showed early on, the sprinkler is very narrowly defined. A UK residential watermist system is also very narrowly defined, as only applicable to automatic mechanical nozzles and as a wet pipe. So this is unfortunately against the principles of even the British standards, which are coded in BS0, where performance requirements should be prioritized over descriptive characteristics, which limit the scope, which is exactly the case here. So if I go back to the ladder analogy, if a ladder is a historically accepted practice to meet the performance requirement of getting to A to B, then what is a lift? If it still meets the requirement of getting from A to B. So unfortunately, due to the over-reliance in guidance documents, lift is very frequently considered a non-compliant ladder. And this is relevant, really relevant, when I talk later about the fitness for purpose and Dame Hackett. So what we argue as innovators is that, in fact, one should be looking at the performance requirements as opposed to which are getting from A to B, right, or B1 to B5. And sure, a ladder stencil should be used if one is using a ladder. But if not using a ladder, then the performance of the lift should be judged by its ability to get to A to B and not whether it fits the ladder stencil, which is unfortunately what happens a lot. Okay, so I now go back to when talking about innovative systems, I'll go back to the performance requirement of suppression systems and how would it apply to innovative systems, given that they're not coded in the specific standards for suppression. Well, the first is going back to the 3 key objectives of suppression. If it's not interoperable, then is it out of scope? And if it's got a different scope, then it's just a different definition and it works on a different principle. On B, the consistency of performance, can you expect the same performance of it? Does it work in a way that the fire test and other performance requirements can be verified, are relevant to be verified? So, and finally, is it a different installation method? And if so, is there a DIOM, an installer, should it use the manufacturer's instruction handbook to be installed? So I'll go back to the 3 performance requirements: the fire test, the water supply adequateness, and the hydraulic calculations, which can all be assessed and verified and third-party verified and certified by third parties with innovative systems. It's literally the willingness to do the due diligence and verify whether it is fit for purpose as opposed to whether it is compliant, whether it fits the ladder stencil. Okay, and what does approved document B talk about innovation? Well, it states that it acknowledges that guidance is at odds with innovation due to its historically based approach, but it also highlights that because just because compliance is declared, it doesn't mean that it's fit for purpose for a specific application. It does require proper due diligence from the involved stakeholders to ensure that they have complied, whether through alternative means or through the common practices. So finally, just to wrap up, I'll talk about a bit about these last few slides, which systems to use, a lift or a ladder that passes through the ladder stencil. Well, we argue that instead of a one-size-fits-all approach, it should be on a case-by-case basis, as Dame Hackett does. And these are some of the variables that should be considered when making that decision. Firstly, the application, the type of fire loads present in the space. This is keen domestic, as the types of fire and fire loads have changed, and more about that later. Second, the ease or cost of install, and many system requires tanks or a significant change in the water supply infrastructure. And maintenance is also a question for there, how frequent and how difficult. This is typically done yearly through and requires entrance into the property so the nozzles can be inspected. Third, are there any other constraints like heritage places or multi-story dwellings with vulnerable occupants where damage and activation and displacement are more disruptive than to the average occupant? And fourth, ensuring stakeholder buy-in. As per Dame Hackett's report, it depends on the occupancy. There needs to be their buy-in, and buy-in includes both disruption in the event of activation. How would the and also in how would the property be disrupted in with the need of maintenance? So going more into the application, the fire problem itself has evolved over time. There are now modern methods of construction. There is modern furniture, there is densification, and there is an aging population. And these all increase the impact of a fire in case it occurs. But at the same time, while there is less smoking and less chip pan fires, there are more electric and electronic devices in the home. There are lithium batteries and there are white goods that create different type of fire hazards in the occupancy. And white goods are becoming a more frequent cause of fire in domestic environments. And when we're developing systems that will tackle these evolving types of fires. So this takes us to building a safer future. The outcome-based approach that makes stakeholders look into the occupancy characteristics instead of a case-by-case basis when defining the right collection of solutions to meet the performance requirements of the building regs. Guidance should not be an excuse to avoid common sense, is what Dame Hackett asks, and that this should be looked on truly on a case-by-case basis. So going back to the ladder analogy, there's occupancy where the risk is not exactly the average risk or occupant, and historical solutions may not be really fit for purpose. So this is exactly what the outcome-based approach seeks to achieve on a case-by-case basis. So how do suppression finally, I'll go into how suppression systems now are being developed to address some of these new issues. Let's see if this video plays. Okay. Well, this is the idea is firstly in tackling modern fires more effectively. This is a comparison between an electronic nozzle and a traditional mechanical nozzle. And white goods create concealed fires, as you can see, which produce a lot of toxic gases and which are difficult to suppress just through wetting. So the targeted electronic watermist can create turbulent, saturated environment that can quickly suppress the fire and reduce heat and smoke production quickly. And its suppression can even extinguish it, can take place even before other systems get to activate. And the loss of visibility is then predominantly just suspended mist in the environment instead of hot, dense, and hot toxic gases that have been produced and then mixed by the suppression system that has taken longer to activate. So just let this suppression activity here finish. Okay. Oops, that played again. And finally, we were, as a research project, we have been recently awarded an Innovate UK grant of £500,000 to experiment two new additions to Suppression. The first is to connect our system to the internet. So this allows it to be allows remote monitoring. So that if a fault is found, which could be through tampering or could be through power loss, for example, that there's an immediate message to address it to the relevant stakeholders, which might include the installer that goes to do the diagnosing and the service only when it is required. This replaces the annual physical inspection with a full-time self-diagnosis and remote monitoring solution, which reduces cost but also reduces disruption to occupants and increases significantly system reliability. This also contributes to the golden thread cited by Dame Hackett, where the digital information for that specific installation, which includes the design and the status of that installation, is all placed in a single digitally easily referenced location on the cloud. And the second activity that we're doing as part of this research project is to determine whether we can use the thermal imaging sensor present to detect whether there's a fire to also observe temperatures in the room and observe occupancy on a daily basis. And this can be used for the fire services so that during their search and rescue activities to help and maximize the efficiency, to maximize the chances of and the accuracy of finding occupants in properties needing to be rescued. But this system can also be used to improve the efficiency of heating systems or even reduce fuel poverty in social housing, for example. So a big reason why commercial suppression systems are on average more reliable than residential is that there's a maintenance manager present in these commercial properties with an incentive of losing an insurance claim in case there's no evidence of maintenance. That does not happen with residential. So what we're trying to do is getting suppression systems to provide value in other activities, such as controlled heating, for example, and that creates an incentive for its proper upkeep and also creates immediate evidence if something has gone wrong with it, which is what, for example, a boiler does today. So this is it in terms of my presentation for today. And if you'd like to learn more, I suggest you go to our YouTube channel. We have lots of videos that show how our system and how suppression works, design, installation, commissioning, and all sorts of other useful information. That's it from me. I'll just have a look at, if you have any questions, please send them over and I'll be happy to answer them. Okay, I have a question here being asked. There's a question regarding whether there's a Legionella risk with suppression. Well, generally there isn't a problem with Legionella, given that Legionella requires visible light for it to be developed, so that given that the water is stagnant in pipes when it is a wet pipe system, the Legionella is not a risk. The only risk, of course, is corrosion or biological growth in the pipes, which, if the system is discharged, that will all come out from the sprinkler head or whatever the discharge method is. But our electronic system, for example, uses a dry pipe so that there's no water retained in the pipes. And curiously, it's even used in in ski locations where there's a risk of freezing, so that the dry pipe does not also create a risk of the pipes freezing as well and not being able to operate, or worse than that, creating an escape of water issue because the pipes have cracked. Okay, I have another question here, which is what do I think needs to be used to encourage and use more innovation in the fire sector? Well, to be honest, I think that Dame Hackett really nailed that in that by creating the building safety regulator, the responsibility of ensuring that buildings are fit for purpose in terms of fire safety is now on the hands of the responsible person of that building, which might be the building safety manager or the person assigned to do that. And that means that obviously it will be evident that many of the buildings are not fit for purpose in terms of fire safety. And because they are occupied and they're existing buildings, I'm sure, and that they have to provide evidence to the building safety regulator that the use of, as opposed to necessarily following guidance document, the fire risk assessment approach will in itself allow the use of innovative systems. Even the fire safety order has as one of its clauses that the stakeholder should adapt to technical change, which in effect means adapting to innovation and the different ways in which issues can be tackled. So effectively, fire risk assessments and the fire safety order addresses issues with existing buildings in the opposite way that the approved document B does, which is not asking to use necessarily historically common practices, but to prove that whatever solution that you're proposing is the adequate one and that the risks have been adequately mitigated. So I do think that there's going to be once the building safety regulator is implemented, there is going to be a massive use and development of innovation in the industry. I guess that's in part why we're a big fan of Dame Hackett, by the way. Okay, we're running out of time. I can take one more answer. I'm receiving a few messages here of projects that we might be interested in having a look at. And yes, as a few of you have left their email on the dialog box here. We'll be happy to follow these up and look into different projects or whether it's a suitable application for a start. That's what we like to do. Feel free to provide your contact detail if you'd like us to look into specific projects. Also, if you have any specific questions about our product, if you go to our webpage, we have a support page and you can just ask any questions. We have a vast database of answers where there are many answered questions which are frequently asked about our product as well as about suppression and suitability of systems generally. Okay, I'll take one last answer. One last question. Let me see here. So I'm being asked here about third-party certification and why UL, why going to the US. So we found out that although UL is an extremely expensive place, it is the most recognized international lab for fire safety, but also for product safety. And surprisingly, you'll find that at the back of every computer phone, there is a UL or UR mark, which is evidence that your product is electrically safe. So we've gone there as the more innovative, happy lab internationally to certify systems, and we're doing this over the last 3 years, and we expect to have that completed at the end of this year as the fully certified system through UL. And UL is present in the UK, and I've been told that it's going to be much more present in the UK post-Brexit, given that I think the UK wanted an excuse to get closer to the US, which means closer to UL as well, yeah? Okay, well, I think that's it in terms of questions and answers. Thank you very much for your time. Bye-bye.